Today we are explaining the paper Rational Rewards Reasoning Rewards Scale Visual Generation, both training and test time.
Give me the big picture first.
The paper starts from a simple complaint. Visual reward models usually collapse rich human judgment into one unexplained number. Rational Rewards forces the reward model to write a structured critique before it assigns scores. So the model says what is wrong with an image instead of only outputting a scalar. That turns the reward model into a tool for two jobs at once. Training generators with better rewards and improving a single generation at test time by rewriting the prompt after seeing the image.
What was wrong with the earlier reward model setup?
The paper points to two concrete problems. First, a black box scalar reward is easy to aim, because the generator can push the score up without actually fixing instruction faithfulness, physical plausibility, or text rendering. Second, a single number gives no actionable feedback, so it is weak both for reinforcement learning and for correcting a bad sample after generation. The authors also note that collecting high-quality human-written rationales at scale would be too expensive, so they need a way to recover reasoning from preference data that already exists. Let us look at the method overview next.
What are the two optimization paths in this design?
The left side is parameter space optimization. There the critique is converted into dense rewards for reinforcement learning, with separate signals for dimensions such as text faithfulness, image faithfulness, physical quality, and text rendering. The right side is prompt space optimization. After the generator makes an image, Rational Rewards critiques that exact output, rewrites the request to fix the observed weaknesses, and asks the generator for one more try, so the same reasoning model can either shape the weights during training or steer a single sample at inference time.
You mentioned PAROT. How do they train this without paying for human-written rationales?
PAROT. The teacher model first sees a pair of images together with the known human preference and writes a rationale that justifies that label. Then a consistency filter keeps only rationales that still let the teacher recover the preference when the label is hidden. Finally, a smaller student model is distilled on those filtered rationales, so at deployment time it can generate critiques and scores without being handed the answer. In other words, the paper converts cheap pairwise preferences into reasoning supervision.
Where does the main equation fit into that pipeline?
This ELBO is the paper's formal bridge from the theory to the pipeline. The first term says a rationale is useful only if it helps predict the correct human preference. The second term says the deployed student should stay close to the teacher's posterior over good rationales. That is why the method has exactly these pieces. Generate candidate rationales, filter them for predictive consistency, and distill them into a model that can reason from the input alone.
What does the consistency filter actually buy them in practice?
It removes rationales that only sound plausible. The paper asks the teacher to infer the winning image from the rationale alone, and only keeps samples that still point to the right preference. About 72% of generated rationales survive that check, which means preference anchoring already produces many good explanations. But the filter still throws away a meaningful block of hallucinated or weak ones. That filtering step is important because the whole system depends on critiques being predictive, not merely fluent.
Before optimization, how strong is Rational Rewards as an evaluator?
The evaluator results are already strong, with a QN3VLP backbone. Rational Rewards reaches 64.2 on MMRB to text to image, 70.3 on MMRB to editing, 66.2 on edit reward bench, 16.8 on Gen OYI bench text to image, and 80.1 on Gen OYI bench editing. That beats the open source scalar reward baselines across the board, beats Gemini 2.5 Flash on several columns, and gets close to Gemini 2.5 Pro while using an open 8 billion parameter model. The paper also says this comes from 10 to 20 times less training data than comparable scalar baselines. Now let us move from judging images to improving them.
What is the clearest train time improvement once they use it as a reward?
On text to image, the paper gives a very clear number. FLUX1 def starts at 60.97 overall on Unigen bench, rises only to 62.55 with multi-reward, reaches 66.71 with a large generic Q13BL judge, and climbs to 70.34 with Rational Rewards. On image editing, Flux1 context moves from 3.5 to 3.8 for an IMG edit bench, beating edit reward guide a day or L at 3.66. So the improvement is not just that the model talks more. The reward actually drives stronger generation quality than the scalar and generic reasoning baselines.
And what makes the test time prompt loop so important here?
Because it gets close to, and sometimes beats, reinforcement learning without touching the weights. The paper says one critique and refined task costs about 0.4 seconds of extra VLM inference per image, compared with about 380 for GPU hours to fine-tune one base model with ARL. On IMG Edit Bench, prompt tuning lifts the ARL tune flux model from 3.8 for to 4.01. On QN Image Edit, prompt tuning on top of ARL reaches for 0.43, slightly above ARL alone at 4.38. On G-Edit Bench overall, prompt tuning also edges past ARL, 8.33 versus 8.29. Let us also look at the reward hacking evidence, because that is one of the paper's main motivations.
Why is this comparison so central to their argument?
Because it shows the failure mode the method is supposed to fix. In the scalar reward run, the training reward keeps rising while the generated images get worse, which is classic reward hacking. In the rational rewards run, the reward curve and the visible image quality move together much more stably. The paper's claim is that forcing the model to justify scores in multiple dimensions makes it harder to exploit shallow shortcuts, because inflated scores have to stay consistent with an explicit critique.
Does the paper admit any limitations?
Yes, the authors say the model can inherit blind spots from the teacher used to generate rationales, and it can also inherit aesthetic or cultural bias from the preference datasets. They also have not done a full sensitivity study of the test time threshold that decides when to refine a prompt, and the evaluations are limited to English benchmarks rather than multilingual or non-photorealistic settings. So the results are strong, but the paper is not claiming universal robustness.
What is the clearest takeaway at the end?
The main takeaway is that reasoning itself becomes a useful optimization interface. By making the reward model explain what is wrong before it scores, the paper gets a better evaluator, a more reliable ARL reward, and a test time prompt loop that can rival expensive fine-tuning. For this paper, the strongest message is not only that rational rewards wins a few benchmarks. It is that structured critique can turn preference data into a practical way to train and steer visual generators.